Pressure is always measured as a difference between two pressure values. The first value is that of the fluid's absolute pressure. The other value is a reference pressure value. When the reference pressure is equal to 0, then the pressure reading is called the absolute pressure. When the reference pressure is the ambient atmospheric pressure, then the pressure reading is called the gauge pressure. When the reference pressure is equal to any arbitrary value other than 0 or atmospheric, then the pressure reading is called the relative pressure between the fluid and the reference pressure location. When the reference pressure is equal to 0, then the pressure reading is called the absolute pressure. Consider a manometer where the open leg is closed, and the gas within it is totally removed. The pressure above that manometer leg is 0, since no gas is present. The liquid height in the manometer then gives a reading of the absolute pressure in the gas tank that is connected to the manometer. The absolute pressure is equal to the density of the liquid times the gravitational acceleration times the height difference of the liquid in the two manometer legs. Up until now, whenever we talked about pressure, what we meant by pressure was absolute pressure. When calculating the properties of a fluid, such as in the ideal gas law, the absolute pressure value is the value that should be used. In gases, the absolute pressure can only be positive. In liquids, the absolute pressure is usually positive, although under certain circumstances, liquids in small diameter tubes can support a negative or tensile stress. This is how transpirational pull works in plants. A negative pressure that can be as high as several hundred atmospheres pulls the water up the trunks of tall trees, in small channels of xylem tissue. When the reference pressure is the ambient atmospheric pressure, then the pressure reading is called the gauge pressure. In other words, the gauge pressure is equal to the fluid absolute pressure minus the ambient atmospheric pressure, and is equal to the density of the manometer's liquid times the gravitational acceleration times the height difference between the liquid in the two legs of the open tube manometer. The gauge pressure can have positive or negative values, depending on the value of the pressure reading as compared to the atmospheric pressure. If we neglect the weight of the column of fluid in the manometer leg that is connected to the unknown pressure source, then the fluid height difference between the two legs of an open tube manometer directly measures the gauge pressure in the leg of the manometer that is connected to an unknown pressure source. If the fluid's absolute pressure is equal to the atmospheric pressure, then the fluid height difference between the two manometer legs is 0. And hence the gauge pressure is 0. It should be noted that the ambient atmospheric pressure in the shown equation is equal to the atmospheric pressure in the location where the manometer is present. This ambient atmospheric pressure value can be somewhat different from a standard atmosphere, or 101,300 Pascal, depending on the elevation, ambient temperature, and weather conditions. In general, however, when the gauge pressure is measured at sea level, the ambient pressure value can usually be assumed to be identical to a standard atmosphere with little error resulting from this assumption. When the reference pressure is equal to any arbitrary value other than 0 or ambient, then the pressure reading is called the relative pressure between the fluid and the reference pressure location. That reference arbitrary pressure can be the pressure at another point in the fluid, or it can be the pressure within another fluid. Consider the shown manometer that has fluid tank 1 connected to one of its legs, and fluid tank 2 connected to its other leg. The fluid height difference between the two manometer legs gives a reading of the relative pressure difference between the two tanks. In this case, it does not matter whether the pressures in the two tanks are expressed as absolute pressures or gauge pressures in the relative pressure equation. This is due to the fact that since the two pressure values are being subtracted, Adding the ambient pressure to both pressure values would not affect the relative pressure result. As we have seen before, the pressure at points A and B that are located at the same elevation in the manometer liquid, is the same. The pressure at point A is equal to the fluid pressure inside tank 1 plus the density of the fluid in tank 1 times the gravitational acceleration times the addition of the heights h and h1. The pressure at point B is equal to the fluid pressure inside tank 2 plus the density of the manometer liquid times G times H plus the density of the fluid in tank 2 times G times H2. We then set the expressions for the pressure at points A and B equal to each other and obtain the shown equation, which can be solved for the pressure difference between the fluid pressure in tank 1 and the fluid pressure in tank 2. The relative pressure can be positive or negative, depending on the values of the two pressures that are being compared. We have seen before how to calculate the magnitude of the force due to pressure that is acting on a flat plane. When the pressure on the plane is uniform, click on the shown link if you would like to review that section now. For a uniform pressure, this force, expressed in vector form, can be written as the negative of the magnitude of the uniform pressure acting on the area, times the vector of area on which the pressure is acting, where the vector of the area is equal to the magnitude of the surface area, times a unit vector, n, that is perpendicular to the area, and pointing away from it. Consider the force due to a uniform pressure that is acting on the flat horizontal bottom of a rectangular container. The reason why there is a negative sign in the vector equation for the force is that the force vector is pointing in the opposite direction as compared to the area vector. If the pressure that is acting on the area is not uniform, the force would have to be obtained by integrating the non-uniform pressure over the area. The vector, small a, represents the infinitesimally small area that is used in the force integration. In this case, the total area, or capital A, is equal to the integration of the area, small a. Consider the case where the rectangular container that was discussed in the previous section is completely filled with a liquid, whose density is equal to ρ. Due to the gradual increase in liquid pressure, the deeper the position in the liquid is, the gauge pressure on any of the container's side surfaces is not uniform. The pressure at any location, that is at a depth, h, below the liquid's surface, is equal to the density of the liquid times the gravitational acceleration. At the container's surface, where h is equal to 0, the gauge pressure is also equal to 0. At the bottom of the container, at a depth, capital H, below the liquid's surface, the pressure is equal to the density of the liquid, times the gravitational acceleration, times the container's height, or ρ times g times capital H. Consider the cube that is filled with a liquid. The force vector that is acting on the container's side wall is equal to the negative of the integration of the pressure times the vector of the infinitesimally small area, small a. Recall that the pressure is equal to ρ times g times h. The area vector, d small a, is equal to the width of the container, w, times d small h, times the unit vector n that acts perpendicularly to the area, Substituting the expression for P and d small a into the force equation, we get the shown expression, which can be simplified and integrated from small h equal to 0 to small h equal to the total container height, or capital H. By performing the integration, we get that the force vector F that is acting on the vertical container wall is equal to the negative of the fluid density ρ times the gravitational acceleration g times the width of the container W times the height of the container capital H squared divided by 2 times the unit vector n.